Hey, welcome to The Explainer. Today, we're going to talk about something really cool. A scientific breakthrough that could take a huge pile of industrial waste and turn it into valuable, sustainable materials for the future.
So let's just dive right in with the big question. And the answer might be hiding in plain sight. You know, in a material that we make millions of tons of every year, and then we pretty much just throw it away or burn it. We're talking about the leftovers from the paper industry.
So our story really begins with this stuff called lignin. It's actually the second most common natural polymer on the entire planet, right behind cellulose. And we make mountains of it as a waste product when we make paper.
Okay, so what is lignin? Well, you can think of it like the concrete that holds the rebar together in a building. It's the natural glue that gives wood its strength and rigidity. But to get nice, soft paper, you have to get rid of it. And once you do, you're left with this incredibly abundant material that has almost no high-value uses. It's a huge missed opportunity.
Okay, so here's where it gets really interesting. The big idea is this. What if we could use all this natural, renewable waste to replace a chemical called phenol? Phenol comes from fossil fuels, and it's a critical building block for all kinds of things. Strong glues, plastics, carbon fibers, you name it. Making that switch would be a massive win for sustainability. But there's a catch, right? There's always a catch. In its raw form, lignin just isn't chemically up to the task.
All right, this slide right here, this is the whole problem in a nutshell. Think about it like you're building with Legos. Phenol, over on the left, is like a perfect Lego brick with 3 open studs, just begging to connect with other pieces. It's super reactive. But lignin, on the right, well, it's like a Lego brick where someone's already put little caps on all the studs. Its connection points are blocked by these things called methogroups, which makes it really hard to build anything with it.
So, the big question is, how do you get lignin to open up? How do you pop those caps off the Legos to unlock all that hidden potential? Well, scientists are turning to a kind of biochemical makeover, using some amazing tools borrowed directly from nature itself.
It all comes down to a process called demethylation, and really it's just a fancy word for a very specific job, surgically removing those blocking methoxy groups. If you can successfully knock those chemical caps off the lignin, you free up its bonding sites, and suddenly it becomes way more reactive and a whole lot more useful as a replacement for phenol.
So how do they actually pull this off? It's kind of like a 3-step recipe. You start with your boring, low-reactivity lignin. Then you add this special biochemical cocktail, this enzyme-mediated system, and boom, out the other side comes a high-reactivity lignin that's ready to go. And the key thing to remember is this isn't just regular chemistry, this is biochemistry.
So let's meet the all-star team, the microscopic crew that researchers from the RISE Research Institutes of Sweden put together to perform this incredibly delicate chemical surgery.
So this LMS team has 2 key players. First up, you've got the laccases. These are amazing little enzymes that come from fungi, and they act as the actual surgeons, making the chemical cuts. Then you have the mediators. Think of these as the surgeon's assistants. They're these little helper molecules that make the laccase work faster and more efficiently. The researchers tried out 6 different combinations of these guys to see which recipe worked best.
And you know what? It worked. It worked beautifully. The results were super promising. But, and this is a big but, they also uncovered this completely unexpected and dramatic side effect that almost wrecked the entire process. First, the good news. And it was really good news. This chart just lays it all out. On the far left, you see the original lignin. It started with a high number of those blocking groups. But check out what happened after the best treatments, like L1-ABTS. That number dropped like a rock. They managed to get rid of almost half of the blocking groups. I mean, that's a huge win.
Nope, not even close. It turns out that while this one, amazing, desirable reaction was happening, another, very undesirable reaction was happening at the exact same time. And it was having the complete opposite effect.
So this sneaky side reaction is called polymerization. And you got to picture it like this. Imagine you're trying to open up all these connection points on individual molecules, which is great. But in the process, you're also making the molecules super sticky. So instead of staying separate and ready to build with, they just start glomming together into this one giant, tangled, unusable clump. That's polymerization.
And wow, this graph just shows it perfectly. See the black line? That's our starting lignin, nice and light. Now look at that red line. That's the sample treated with L1-ABTS, the one that was so good at removing the blockers. See how it's shifted way over to the right? That's a clear sign of that massive runaway clumping. It was basically creating a giant lignin hairball.
So you've got this chemical tug-of-war going on. Demethylation is pulling in one direction, making the lignin more reactive, which is great. But polymerization is yanking it in the other direction, making it less reactive. The real challenge wasn't just to find the strongest treatment, but the smartest one, the one that found the perfect balance.
And this table just lays it all out beautifully. Look at L1-ABDTS up at the top. Demethylation, very high. Awesome. But the polymerization, extremely high. Total disaster. But now, look down a bit at L2-HBT. The demethylation is just as high, but the polymerization, just moderate. That was the sweet spot they were looking for.
And that's really the big lesson here, isn't it? Sometimes most powerful isn't actually best. The winning formulas L1-TEMPO and L2-HBT came out on top because they did the job they were supposed to do without causing this massive clumpy side effect. They struck the perfect balance.
You know, the researchers themselves summed it up perfectly in their paper. They said there are these two competing reactions. One increases reactivity, and the other one, the clumping, has the exact opposite effect. It just nails the central puzzle they had to solve.
So what does all this mean? It means the secret to our next generation of green materials might not be about inventing something totally new from scratch. It could be hiding right under our noses, in the stuff we've been throwing away for decades. By getting clever with chemistry, we can get one step closer to a true circular economy, where one industry's trash really does become another's treasure.